first lecture I didn't finish what I planned, so things moved slowly. And I was looking at the slides and realized that there are several results I want to talk about and not much time. So today I'll be spending less time on explanation of the not even hand-waving about the proofs, but mostly stating results. I promised to several people in the audience to talk about several things. I want to be able to touch upon those different things. And then if anybody is interested about details of how something is proved or why is it true, then I'll be more than happy to talk afterwards. So it will be a lot of results coming up. Please forgive me for that. Otherwise I'll run out of time. So what I want to talk about today are the exact reconstruction formulas, and then a little bit about the incomplete data problems where you have limitations on the radius, or which for circular transform radius, but for the imaging applications is the time or the depth of penetration, and then hopefully I'll have some time to talk about the range. So first of all, I want to talk about the exact reconstruction formulas. Yesterday we spent full lecture to talk about injectivity. So I was telling you that if you have this type of set, then you can recover the function uniquely. If you have this kind of set, you cannot recover the function uniquely. But we never said, okay, let's say you know that you have uniqueness. How would you do that? For example, we had one result that said in 2D, every closed curve, if you have all the radii, every closed curve for the location of the centers would be a set of injectivity. And we said that, for example, in medicine, that would be good enough because you would put the microphones all around the body. That would be a closed curve, hopefully very well sampled, and then you can recover the function. But those results didn't tell us how. So there are exact reconstruction formulas for the circular radon transform, but for a very few geometries are these results exact, and those few geometries are circles, squares, rectangles, lines, and planes, depending on which dimensions you are. And if you think about it, it's not surprising. The reason is that if you remember from the regular radon transform, we said that the way you can get these formulas is that you utilize certain symmetries or certain invariances. Remember, for the regular radon transform, we had shift invariance, we had rotation invariance, we had dilation invariance, and because of rotation invariance, we had Fourier series approach. For the shift invariance, we had the Fourier transform, and then for dilation, we had something with Mellin transform, and so on. So the same thing here. If you think about all these shapes are the shapes that would give you some sort of invariance, and that sort of invariance would allow you to get certain types of exact reconstruction formulas. And even for these few geometries where we have certain invariances and we have exact formulas, those exact formulas are often limited to certain support situations. So for example, the very first one I want to talk about is the circular geometry. So let's say the function is supported inside the disk, and you have your microphones on the edge of that disk. So you're sitting here, you collect the integrals of your function along these circles. I'm skipping the outside because I'm assuming my function is supported inside. So let's say you have all the locations of the centers and all the radii. Can you recover the function? You can think of this problem in 2D, or you can think of this problem in 3D. Where you have a sphere and your integrals are along the spheres. So here is the first result. The result is due to Professor Rakesh, David Finch, and Sarah Patch from 2004. This is that paper that I mentioned during my previous talk. One of the neat results there that says that if you have this RF is your spherical radon transform, we're in R3 here. So if you have your spherical radon transform, you can recover your function from a formula like this. I want to stop a little bit for a second and geometrically explain what is happening here. So again, you have RF, PR, right? So P is, it's a vector. P is the vector that indicates the center of your integration sphere. R indicates the radius of your sphere. So what it says is if you want to recover the function, let's say this is x. let's say I want to recover my function, the value of the function at this point. So in other words, I want to know the color of this pixel. So what do I need to do? It says that you have to average, so this integration is averaging, with some filtration. So this and the differentiation is filtration. So for a second, forget about the second derivative, forget about this component here. Let's see geometrically, what do you do? Let's assume that you're just taking the integral of the RF itself. So I'm averaging my data, and how am I averaging? Look, he runs the full set, so you're going around the whole sphere. So you have all possible locations for the center. So you have this location, those locations, so on. And for, maybe I have to make it, maybe it's better to make a different picture. So let's say this is X. I go through all possible locations. And then for every location, I choose only one sphere. So if this is my location, what sphere do I choose? In other words, what radius do I choose? The radius is the distance between X and P. So I choose exactly this sphere. So when I move to a different location of the center, I choose a sphere of a different radius, but that radius is chosen so that the sphere goes to this point. So if you are sitting at this point, it's a smaller sphere, but it's like this. So look, what you're doing is you're averaging your data along all spheres that pass through that point. And if you remember, this is exactly what we were doing in the case of the regular Radon transform. Remember, we had the dual of the Radon transform that we called back projection. And what back projection was doing was it was choosing all the lines that would pass through that point. For every line you had data, and you were averaging that data. So here we're doing absolutely the same thing. And in fact, this back projection operator that I'm describing geometrically happens to be the dual operator of your spherical Radon. So you are, in fact, after you have your Radon transform, you're doing back projection, and in the middle you have filtering. If you remember, for the regular Radon transform, we had RF, then we had a filter, then we had R sharp, and then, or R star, or whatever the notation was. And we had different types of filters. So here too, I didn't have time to write all possible formulas, but there are several ways of filtering. One filter, which is between R and its back projection, is you take second derivative with respect to the second variable, and then you have this weight on it, and then you do back projection. That's one filtering. In the same paper, there is another version of the filtering where you do Radon back projection and you filter outside of it. At the end, that was like a Laplacian type filtering, and there are some other options. And by the way, the paper has the inversion formula for all odd dimensions. It's not just 3, it's 3, 5, 7, whatever, all odd dimensions. I just chose 3 because it's more visualizable. The interesting thing here is that the formula works when the function, as I said, is supported inside. If you allow the support of the function to stick outside, even if it's compactly supported but it sticks outside, it's easy to construct a counterexample that shows that the formula doesn't work. So,
but there'll be non-uniqueness.
Well, no. You have uniqueness by Aronofsky-Quinto or by Kuchman's result, right? If you have all the radii. Yeah, right. I mean, or let's say you have the radii from 0. If this is 1, let's say you have the radii from 0 to 2, just enough to reach the edge. But if you have some support here, you're simultaneously touching both sides, right? So the location of the support matters, and the reason this is important, remember at the very first lecture I was showing you for this example of intravenal ultrasound, where there was a catheter in the vein, and you were collecting the data along this circle, but the image was outside. This is the cross section of the artery. This was the catheter, and you were trying to recover the plug on the walls, right? So there may be situations when your support is outside. And then if you think of the situation when the airplane was flying over the ground and you have the circles on the ground, you don't have any, support is everywhere. You're flying, the support is on the left, the support is on the right. They get smart in radars, and they kind of physically shield it so they're looking only sideways. They're only looking at half circles. Then they fix it. But if you allow the support to be on both sides, then that's another tricky situation. It is interesting that, so here's a result by Professor Rakesh, David Finch, and Marcus Hoffmeyer. The third author is different here. This is from 2007. And if you look at this, this is the result for R3, this is the result for R2. And somehow you would think that R2 would be easier than R3, but in fact, if you deal with wave equation, you know that odd dimensions are usually easier than the even dimensions. So, and if you look at the formula, you also can notice that the formula is somewhat more complicated. And again, I want you to think about this geometrically. Look, you have, of course, the function, the dimension of the function here and the dimension of the data here was the same. But look, you were averaging only over the spheres passing through the point. You were not averaging over all possible spheres. Right? If you look here, I was averaging. There was a fixed point, and I was averaging over all points, all spheres passing through this point. Let's look here, guys. Here, again, you're recovering the function from its Radon transform, circular Radon transform. Everything is the same. In fact, this picture represents this better than that because it's a 2D picture, right? So the picture works. But look what you're doing. You're averaging over all possible spheres because you're integrating for all possible angles and all possible radii. 0 and 2 is enough. Because if you're supported inside, the radius is 1, 2 is exactly enough for you to reach the support the last time. After that, it's 0. So you use all of them. If here you were only using some of them, in the 3D case, here you're using all of them. However, look here, guys, you have a logarithmic weight here, and that logarithm, of course, when the argument is 0, the logarithm shoots to infinity. Look at this. When is the logarithm 0? The logarithm is 0 exactly when r is equal to mod x minus p. So you're integrating, you're averaging all your data, but you're using, quote unquote, you're using infinite amount of information when you are close to the circles that pass through that point. If this was a delta function, you would have exactly back projection formula in the usual sense of the word. But that's not a delta function. It's kind of like delta function, right? At the 0 of the log, it goes to infinity. So this is a little bit more complicated version of the back projection formula. And again, in this paper, the result is true for all even dimensions. I'm writing it for 2, but it is true for all the even dimensions. And there are some other versions of the filtering. Again, now the filtering is mostly outside. If you don't look at this weight, then you can push it inside, keep half inside, half outside, and so on. There are different versions, and some of them are better in some situations, where others are better in other situations. But again, pay attention that this is true where the support is inside the unit disk. And in both cases, we're using all the radii. Okay, as I said, 0 to 2 is not limiting. It's the same thing as 0 to infinity. So, and I didn't talk about, maybe I should have started with this. So, look, guys, here there is rotation invariance, right? Because if you have a function, some function inside here, you can first rotate the function, take the Radon transforms, or you can take the Radon transforms and then rotate the data, because the Radon transform, in this setup you can actually, use the, what am I using? Rho and phi. So if you're on the circle, you only need, in 2D for example, you only need the polar angle to indicate the location of the center, and rho would be the integration radius. So the data in the circular setup can be parameterized in 2D by 2 parameters, the angle of the polar angle of the location of the center and the integration circle. So you see, it doesn't matter if you first rotate the picture and then take the transforms, or you take the transforms and then add the corresponding angle to your data. So you have rotation invariance in this setup, and we have already seen before that if you have rotation invariance, Fourier expansion may be useful. You can do something with Fourier series. Remember, in the regular Radon case, we had those Cormack type inversion formulas, and I said that was the Nobel Prize winning work. That's how they inverted the regular Radon transform. So there is a Cormack type inversion formula for the circular Radon transform, done absolutely the same way. So you have a function defined on the plane. You use its polar coordinates. You expand your function into the Fourier series. Of course, your Fourier coefficients would depend on the radius. Then you take the Radon data. Again, phi only tells you the location of the center. Let's say that's a unit circle. Rho tells you the radius. So you can expand the data into Fourier series with coefficients depending on the radius. And now the hope is that, remember, theoretically, G32 can depend on all F1, 2, 3, 4, and so on, and the other way around. But because I have rotation invariance, my hope is that my operator diagonalizes, so that Gn depends only on Fn, Fn depends only on Gn. And it is exactly what happens. This is a work from 1980 by Norton that says that if you write down all your equations, you will see that the nth Fourier coefficient of your function depends only on the nth Fourier coefficient of your data. HNs here are the Hankel transforms. Jn is the Bessel function of first kind of order n. And then the goal is, of course, to solve this equation with respect to Gn. So this is what you measure. This is what you want. Sorry, this is already this is already the result. I thought I had two equations. Okay, and so this is already resolved. There is a version. I should have first written Gn in terms of Fn and then resolve it, but this is the resolved version. Doesn't matter. So this is what you measure G, then you find its Fourier coefficients, then you can express the nth Fourier coefficient of your function through nth Fourier coefficient of your data by this formula. If you haven't seen Hankel transform, here is the definition of the Hankel transform. And again, in this setup, we are requiring the knowledge of the data for all radii. I'm emphasizing this because in a couple of minutes I'll be talking about the situation when you don't have all the radii. Several of you have been asking about the use of Hankel transform in radon-related things. So this is one of the places where it appears. So if you are in 2D, if you are trying to find the inverse of the circular radon transform, then the Cormack type formula involves the Hankel transform. Now, the formula was known in 1980, but nobody has been using it for 25 years or so. The reason for that is that the Bessel functions have infinitely many zeros, one of the reasons. And then you're dividing by a Bessel function, and numerically it was very unstable and it wasn't clear what to do, in addition to the fact that typically the series expansion type formulas are not as good as back projection type formulas for numerical reasons, because you'll have to decide where to cut your series, approximate things, and so on. I'll show you later that in a very recent work with Leonid Punyansky, we came up with a way to deal with the zeros. Basically, the Hankel transform, as you see, integrates from 0 to infinity, and the zeros of the Bessel function are all on the real axis. So it turns out that if you do the contour integration, and instead of going through the real axis, you go and do your integration in the complex plane, you can avoid the zeros and use some equivalence to make things work. So again, yet another example that when you think something is purely abstract, all this contour integration in the complex plane happens to play a role in tomography and numerically for doing computations. So, and also, please keep in mind this formula, because if I have time later, I'll come back to talk about the range description of the spherical transform. This formula is going to be very handy there. Okay, so now I want to talk about a little bit about the situation when you don't have all the radii. So let's imagine, guys, that this is a cross-section of a patient's head. Okay, so let's say I want to image the hand. Now, all these formulas were telling me that I can do everything nicely. The function is supported inside. The dashed red is basically the edge. That's where you put your microphones. But if I want to have all the radii, what that means is that I have to have the data integrals along this, along this, along this, and all the way until I reach here. Now imagine this is the bone. Right? So if you're doing ultrasound reflection tomography, hoping that your ultrasound would go penetrate the bone, go hit some muscle there, and then come back through the bone is not realistic. There may be some metallic implants and so on, and then there may be some other reasons. So I'm just trying to justify the mathematical problem of now you trying to recover the function. Assume you have all the locations of the centers, but you don't have all the radii. Or let's say there is no bone. These signals are very, very weak sometimes, right? So you can only go up to a certain depth. the depth is not infinite. In fact, for ultrasound tomography, for photoacoustic and thermoacoustic, 4 or 5 centimeters is as deep as they can go. So even if there is no obstacle, after a while you cannot go there and come back. So the question is, okay, let's assume I only want to know my function in a certain annulus. Let's say I don't care what happens at a certain depth. And I have enough data to reach the depth that I'm interested in. Can you recover it? So sitting here, you cannot reach there, but you can reach all the way up to here. Can you recover the function in the shaded region? And the answer is yes. And that's what's stated in this theorem. So if you have a function and you assume that function is supported in an annulus from epsilon to r, if you have the radon data, circular radon data for all angles, but for the radii from 0 to r minus epsilon, then f can be uniquely recovered. And the way we proved this theorem was also using this Cornac approach. We were using the rotation invariance. Now, as you can imagine, nothing is free, right? If you're giving up data, then you will have to get something more complicated, because if you were using the whole data and you already had this kind of stuff, which is not easy itself, then you're giving half of the data, you don't expect things to be easy. So here's what I was looking for in the previous slide. So this is the relation between Gn and Fn. This is the Fourier coefficient of the data. This is the Fourier coefficient of the function that I'm interested in. And I still need to solve this. This is unsolved yet. This is what I want. This is what I measure. It's an integral equation, Volterra equation of first kind. This T is the Chebyshev polynomials. You have already seen this in the Cornac formula. And all these complicated things. Everything else is well defined. R is the size of the disk. So if you want, you can think of capital R being 1. Right? So you can rewrite this equation in this form, where I have just hidden all the big expressions into certain things. It's a weakly singular kernel. This thing is basically what you're interested in. This capital Fn is a modified version of your little m. So this is what you know, this is what you want. And you want to solve an integral equation. This is fairly standard. It's Volterra equation of first kind, as I said, with weakly singular kernel. There is a standard procedure how to deal with this. So through this iterative process of successive approximations. So this thing is also something that if you know little gn, then you measure this capital Gn. These guys are going to be playing a role in our resolvent kernel. I don't expect you guys to look at this formula and write it down. I'll give you the slide, so please ignore this. I'm just trying to show you that this is not something simple. So this is the final version. You can recover your Fourier coefficients of the image function from the Fourier coefficients of your data using this resolvent kernel, and that kernel is computed as a series, and that series itself inside it uses some complicated formulas. So this is a nightmarish thing. In fact, Shovik Roy, who is here, has been working with these things numerically. He is doing some really nice reconstructions with the original thing from here. He is doing with another method, but trying to apply this complicated things is not easy. So far, there are some issues that we're trying to deal with. Venki and Praveen, and I think some other people may have been working on this one. So I've been torturing several people at this institute to see if they can do something, and they have been doing wonderful stuff so far. So there may be some good stuff coming out. Okay, so here is a similar result, but the important thing about this is now the function is supported outside. Remember all the nice formulas that we had, the Norton's formula and the back projection formulas by Professor Rakesh and colleagues. They were all working when the support is inside. Now, again, the red dashed line indicates the locations of the centers of the integration circles, and the function is supported in the shaded region. And the answer is again the same. You don't really need all the radii. So if your function is supported in R3R, then you can recover the function uniquely if you have all locations for the centers, and if you have your data, where is the data? There, for R from 0 to R1. So if R1 is any number between 0 and 2R. So what I'm saying is, if you're sitting here, and you can go all the way to this depth, then you can recover the function into that depth. If you can go all the way up to here, then you can recover the function there. So the amount of data that is available tells you the depth that you can recover the function in. And for the sake of saving time, I'm not going to show you the reconstruction formulas. They're as ugly as the previous ones and as hard. And in fact, there are some other issues. There are issues related to the stability. Professor Bowman has been talking about microlocal analysis and wavefront sets. I'll show you in a couple of minutes why in the exterior problem you cannot expect to see certain things that you would expect to see in the interior problem. And then here are some similar results that Venki and I got in 2011, where we get some reconstruction formulas and uniqueness results when the support is both inside and outside. So again, you can ignore the text. I'll try to describe it geometrically. You're collecting the data along this dashed red line, and what we're saying is, if you start with circles with the radii slightly larger to be beyond the origin, and you go all the way out, then you can recover the function in such an angle. So the green is basically indicating where is the first radius that you start, and you can shrink this all the way to a point. So if your first radius is this much, just to barely touch the green, and then you go all the way out, then you can recover the function in this annulus, which is supported on both sides of the red thing. And this is basically saying what I said, that you can basically shrink this thing to a point. So if you start with the radii just barely outside the origin and all the way out, then you can recover the function everywhere other than in that point, basically, which is useless. I mean, you're not losing much information. Right, so this is a mathematical result. I don't know if I can justify this from the imaging point of view, because as opposed to the previous cases when I was saying I start from a small and I go to a certain depth, here I start from a non-zero value and I go all the way. So that's a little bit from the application point of view not clear, but mathematically it's interesting that, you know, if you consider the whole data, if the support is on both sides, somehow the meaningful part of your data is starting from a certain large value and onwards. Okay, very similar results one can get for the elliptic transform. So far I have not been talking about elliptic transform. The reason for that is there are very, very few scarce results about elliptic transform. In particular, the type of results that I have been showing you with the Fourier coefficients and Froment type inversions, one can do with the elliptic transform. So it's very similar, except I'm integrating along the ellipses. So the foci of the ellipses are here. The center between the foci is on this red dashed circle. If you have this much of depth, then you can recover the function in that annulus. And you have the similar type result to the one that I was talking a minute ago, that you can recover a function supported on both sides of the boundary if you start with ellipses large enough to go beyond the origin and all the way out. The formulas are again not really nice, but as opposed to the situation with the circles, these are, to our knowledge, the only exact reconstruction formulas for ellipses. Every other formula for ellipses, every other procedure is approximate, it's microlocal, recovering only wavefront sets, this and that. I have not seen any exact reconstruction formulas for ellipses other than these. And you see, this is just a very specific geometry, the geometry with the circles. If you go to something more complicated, then it's not clear. And not surprisingly, because ellipses are so much more complicated than circles. Okay, so this is another result related to the ellipses. Several authors, Professor Bowman, Venki, Todd Winter, and myself, where we did an approximate reconstruction formula for the elliptical transform in the circular setup. This is recovering just wavefront sets. So what the formula says is, again, you can read the theorem, but the idea is that if you have a function supported inside the disk, and you consider all the ellipses with the fixed distance between the foci and different locations around the circle, and you allow all these radii, or the minor semi-axis is large enough to start at zero and end up at the end, then if you, for that type of elliptical Radon transform, you can define its L2 adjoint, and that would be, not surprisingly, be the back projection, but the back projection in the elliptical sense. So you would choose a point and then choose all the ellipses that pass through that point and average the data for those ellipses. Then, if you consider this operator R star R, the normal operator, just like we did it for the regular Radon transform, then this normal operator would be an elliptic pseudo-differential operator of order -1. So what that means is the elliptic pseudo-differential part tells you that you don't create singularities, you don't lose singularities. So in terms of the wavefront set business that Professor Bowman was telling you about, you have singularities at this. F has the singularities at the same locations in the same directions as R star RF. So you see, F is what you want. RF is what you measure. So ideally, you would like to have R star -1. And then that would be exactly equal. But instead of that, what we have is some sort of, I don't know, let me put a hat here. That's not Fourier transform, some sort of approximation. This is R star tilde of F. So instead of the exact F, you're recovering some approximation, and the approximation is that this guy and this guy may be different functions, but they have the same wavefront sets. The singularities are at the same locations in the same directions. So if you are a doctor and you're looking at the image, you probably don't really care so much about the smooth parts, like the color of your image. If you see the sharp edges, that's all that you want. You want to see if there is a tumor, you want to see if there is a broken bone, you want to see the boundaries of jump discontinuities and the way they are, rather than the color of those boundaries. Right? So you can ignore the smooth part, but if you can recover the sharp edges, then that's good enough. And here is so that's the corollary. This is basically what I was telling you about. And this is the type of, I didn't show the phantoms, but basically we started with an image where you had a circle and two smaller circles inside, and this is the recovered version. So you can see that, okay, I should have probably the original one, but we're recovering the location of the singularities and the edges pretty well. And this was a similar thing with a rectangular object, and we recovered that rectangular object pretty well. This numerical things, in fact, had a filtering that I'm not discussing here. So between R tilde and R star tilde, we had a filtering which was similar to the filtering for the spherical transform. Okay, so I want to talk a little bit about numerical implementation. Well, I won't go to the theory, but I want to discuss the microlocal things with the exterior problem. So this is the formula of Norton that you have already seen. This is how you recover the Fourier coefficients of the image function from the Fourier coefficients of the data. And Norton, in 1980, when he wrote his paper, he claimed that the formula works only when the support is inside. And when we were working on the numerical implementation, we started redoing all the equations, and it turns out that the formula works just fine if the support is both inside and outside. But again, as I said, you have to have all the radii. So if you have all the radii, you can use this formula inside and outside, assuming you can make it work. So here's some numerical implementation, and probably I'll have to do some sketches on the board so that they make sense. Because it's a little bit too dark. So the function is supported in a circle that you cannot see that circle here. It's something like it goes somewhere here. So there is one object here, and then there is another object outside. The other object somewhere here. So let's say the function is 0 here, 1 here, and 1 here, and 0 everywhere else. And you are collecting your data like this. You're sitting here, and then you measure the integrals. And then you're sitting here, and you're measuring the integrals, and so on. Right? So you try to recover this object, the function 0, 1, 1, 0 everywhere else, from the integrals along circles. And if you follow the lecture of Professor Bowman, what he was saying is that you can recover stably. The wavefront sets of the circular Radon transform includes the wavefront sets of the function itself for the situations when you can tangentially touch the edge of the support. So let's look at this, guys. When I'm sitting here, what is the edge? So these are where the singularities are. These are the edges of the jump discontinuity. So it's this boundary is what I'm trying to recover. So if with the available circles of integration, you can touch tangentially those boundaries, then the theory that Professor Bowman has been teaching says that you should be able theoretically, numerically to recover it. So see, this part of the edge is okay, and this part of the edge is also okay, because if I'm sitting here, I can touch it tangentially. This part of the edge is okay, because if I'm sitting here, I can touch it tangentially. These parts, however, are not okay, because, see, in order to touch this thing tangentially, your center of your circle, basically draw a normal to the boundary of the circle. You draw a normal, that never passes through a location of your microphones. So you basically draw normals to your circle. If the normals to your circle hit the location of a microphone, you can recover it. If the normals to the circle don't hit the location of the microphone, you cannot recover it. So for the interior problem, you can recover everything, because if you're sitting here, every normal somehow goes through a location of a microphone. In the exterior problem, imagine you're trying to recover this object. If you draw a normal, you don't have it. You don't have that data, you cannot do anything. So if you look here, this is the phantom, this is the original image. It was 1 here and 1 here and 0 everywhere else. So this is the color code. So 1 stands for this dark maroon and blue is 0. And this is our reconstruction. So you see, this guy has been recovered pretty well. The colors are different here, but the color code is also different. So we have recovered the function okay here. This function, however, you see these edges are nice, but these edges are blurred, because the theory already tells you cannot do that. Now the same thing here, I think the circle was somehow like this. You see how these edges of the reconstruction are blurred, and then these edges are blurred, because if you draw the normals to this big circle, they don't go through an available location of a microphone. But the ones that you draw normal, they come to your circle, you can recover them pretty well. And the thing is that it's not about the method that you use. You can try to recover it with Cormack method, with filter back projection method. It's not about the method. The data is not there. You can use whatever method you want. You're not going to be able to recover these edges, because you just don't have that data. So that's one of the really cool things about the microlocal analysis that Professor Bowman was teaching, that you can tell ahead of time, way ahead of time, what exactly you can expect to do reasonably well and what you cannot do, no matter how hard you try. Okay, so I want to switch gears and talk a little bit about the V-line Radon transform, and then at the end I will come back and talk about range for several different transforms. So the V-line Radon transform is again this transform that integrates along broken rays like this. And if we're in 2D, I would like to have a two-dimensional family of V-line transforms. And the one that you have seen so far was the one in the work of John Schottland, Florescu, and Markel, where they had a rectangular slab. They were entering the boundary perpendicularly, and they were fixing the scattering angle. So they were assuming that the scattering can happen, the ray can break at any depth, but they all break under the same angle. And they had a reconstruction formula for that. So as with every other tomography, typically people try something in the square or rectangular domain and also in the circular domain. And we decided to see what we can do for the circular domain. So just following up exactly what they do, we assume that the rays enter the domain perpendicular to the boundary, just like here, normally to the circle, and then we assume that they all break under the same angle. So let's say you enter here and you immediately break, or go here and break, and then, or enter here and break, and so on. So you enter at different locations, you have the polar angle of the entrance location, and then the distance that it takes before it breaks. And we wanted to see if we can do something good out of it. So the first one is very easy, toy example that is a geometric observation, that if you have all the data, so if you can start here and break, and then, or go and break, and all the way up until you reach here and break, that basically the very last one, the ballistic regime that goes through, corresponds to the radon transform flying through the origin. All the others are simply broken ray transforms. If you have all the data like this, and if we assume that your function is supported in a smaller disk, so you see, if you draw a normal, this is the size that I want. So if you assume that your function is supported only in a disk of this size, then you can recover the function uniquely. How? Well, you can basically get the regular radon data from this, because if you have all of this, look at this. So let's consider this transform, like integrating along this broken ray, and then integrating along this broken ray. So this one and this one, their sum is the same thing as the sum of the integral along this line and along this line, right? It doesn't matter, it's additivity of your integration. So, but then the integral along this line passing through the center is something that you have. So by adding the integral along this, and then subtracting the integral along this, you already have generated the integral along this line. And with a similar strategy, you can generate the radon data, the regular radon data, for all the lines that are going through the smaller disk. And then you use the radon inversion formula. This is just the same thing you have seen, the Hilbert transform and so on, to recover your function uniquely. What are the limitations? Well, of course, the limitations are, first of all, that it's artificial to assume that your function is supported only inside a smaller disk. And then you're assuming that you can go all the way. It's a lot of depth to cover. So what happens if you don't have that much depth? What happens if you have less depth? And I'll be talking about that in a minute. But before going there, I want to talk about one more thing. So imagine, as I said, I have radon data for all the lines that pass through the interior circle. So let's say I have all lines under all possible angles, but somehow passing through this small interior circle. The question is, well, I know that's not enough to recover the function everywhere, but maybe I can recover the function only in the smaller disk. And this is the classical interior problem, which is for example, covered in Natter's first volume. And the answer to that is no. This data is not unique. So remember, several of you have been asking about injectivity for partial data. So this is a classical partial data problem. So if you have only lines passing through a certain region, but all of them passing through that certain region, can you expect to recover the function at least in that certain region? The answer is no. And so in this setup, you may say, well, okay, maybe my function is not supported in the smaller disk, maybe it's supported in the larger disk, but can I at least recover the function in the interior? The answer is no. So what happens if we want to have, so there are these issues with the support. Interior problem is not well posed. You don't have a unique solution. And then why can we hope to still be doing well? We can hope to still recover something because I'm losing information. Why am I losing information? Well, I have the information about this transform separately. Then I have the information about this transform separately, but I never use them. I actually add them up. And when you add them up, then you subtract something else and so on, you lost information. Right? I mean, you had 1 and then you had 3 and you added and the answer is 4 and now you cannot go back. If you know 4, was it 0, 4, 2, 2 or 1, 3 or 3? Right? So addition loses information. So then maybe one can do better without loss of information, and the key here would be rotational invariance. And rotational invariance is something that hopefully is easy to see, that you can first compute your data for different angles and then rotate in your data, or you can rotate your function and then collect the data. So there is rotational invariance in this setup, so maybe one can do something with the Cormack inversion approach, do something with the Fourier coefficients. And it turns out that it is indeed possible. So, and I'm going to use even less data, only half of the data. So you have a function supported inside the disk, so it's from 0 to r. Now I don't make any exclusions for being close to the boundary. Then f can be uniquely determined from its broken ray radon data, and you see I'm using only half of it. So I'm going to use broken rays only before you reach the center. I don't want to use anything further. With half of the data, no restriction on the support, you can still recover the function uniquely, but as usual, you cannot do it for free. The formulas will be more complicated. So just like before, you expand the function into the Fourier series. You expand the data into the Fourier series, and the hope is that the corresponding Fourier coefficients would depend only on each other. And it turns out that they are related by a Mellin transform. So the Mellin transform of your image function is related to the Mellin transform of your function and some function Hn. This is a complicated function. It's on the next page, so I just wanted it to be in a clean form. And the Mellin transform has a known inverse. So here it's written, so you can get the Fourier coefficients of your function from the Fourier coefficients of the data. And I know somebody else was asking about Mellin transform, so here is one place where you can look at the applications of Mellin transform to tomography. And here is the function Hn. It's ugly and complicated, but the good thing about it is, you say, for example, if you're writing a code, you need to program this only once. It does not depend on f, it does not depend on g. It's just some complicated function that you code, put it as a file, a bunch of numbers in your computer, and then you can use it for all different pairs of fn and gn. Okay, so in the final 10 minutes, I'll talk about the range description for the Radon transform, and then for the spherical transform. The importance has been already emphasized. The inverse only works on the range. If you're outside of the range, you may have issues. Sometimes in these incomplete data problems, when you don't have certain data, what people do is they zero field. So you just basically substitute everything by zero. If you know something about the range, you may do it in a smarter way. You can use the range to suppress the noise and so on. So what is the range description of the regular Radon transform? There are certain things that we have already discussed, certain properties for the function that is a candidate for being the Radon transform of somebody. So if you have a function g of omega t with omega on the unit circle and t an arbitrary real number, when can we say that it is a Radon transform of some function f of x? So first of all, you already have seen evenness. So the evenness is one of the conditions. If your function is not even, it cannot be the Radon transform of another function. The other thing is that this is something a little bit more complicated, but I haven't shown the proof. But you can show that if your f of x is decaying faster than any polynomial, say if it's in the Schwarz space, then the Radon transform is also in the Schwarz space, so at infinity it decays faster than any polynomial. And then this is some interesting algebraic exercise that you can make. It's actually written here that if you consider the moments of your Radon transform, the moments, this is a definition. So your Radon transform depends on the angular variable and this distance variable. So if you multiply to kth degree of the distance variable and integrate, it is called the kth moment. So it turns out that the kth moment of the Radon transform is a homogeneous polynomial of degree k in omega. So here it is. So this is the definition of the Radon transform. So one line, and you can see that this thing is a homogeneous polynomial of degree k in omega. It is not true for arbitrary function. So if you arbitrarily write some function with certain smoothness for omega in S1 and T in R, this thing is not going to be satisfied. So okay, so there is one condition here, the evenness. This is the other condition that if you are seeing the first time may look something strange. But the really cool thing is, it turns out that these are also sufficient. So these conditions are not only necessary, but they are also sufficient. In other words, if you take a function g with this kind of variables and smoothness, then if they are satisfying these two properties, there must exist a function f for which Rf is equal to g. So these two conditions are the necessary sufficient conditions. This is the description of your range. For the spherical Radon transform, there are some results for the range description, but it's interesting that even those results are for very, very special geometries. In fact, the circular geometry is one of the few cases where the range is completely known, and the range of the the description of the range is done in the Fourier domain rather than in the time domain. So because of that, I want to look also at some type of description of the range of the regular Radon transform, but in the Fourier domain. So this is a theorem that I said. So that G, if it's smooth and compactly supported, then evenness and moment conditions are necessary and sufficient conditions for it being in the range. And also the same thing is for Schwarz space. Here it's compactly supported. You don't have to have compactly supported. You can take Schwarz space and it would still hold. So, okay. So let's go to the range description in the Fourier domain. So I'm going to use the Fourier slice theorem. Remember, these two-dimensional Fourier transform of your function is equal to the one-dimensional Fourier transform of the Radon transform. So now, look at this, guys. If you think of this as a function in Cartesian coordinates, which it is, right? This is sigma times omega. This is a vector, so it's x1, x2. On the other side, you have a function in polar coordinates. And you want this thing to be smooth, right? Because it's a Fourier transform of something that is compactly supported, or say in Schwarz space. So now here's a question. You can forget about the Radon transform. This is a question that you can give to any calculus 2 student. You have a function, say, I don't know, h1 of rho phi. And this function in polar coordinates. This function is smooth in both coordinates. Rho from 0 to infinity, phi from 0 to 2 pi. And then there is the corresponding change of coordinates that would take you to the Cartesian coordinates. What condition would guarantee that your function is smooth in Cartesian coordinates? If it's smooth in polar coordinates, does it mean it's smooth in Cartesian coordinates, or there may be some issues? The origin. You may have issues at the origin, right? Think about it. If you write a function in rho and phi, and if your function is smooth in both in rho and phi, would that function be smooth on the plane in terms of x1 and x2? Except possibly at the origin. At the origin, you may have an issue. So it's an exercise. What condition here would guarantee smoothness at the origin as well? And here's that condition. Smoothness at 0 in Cartesian coordinates implies that if you take the kth derivative in this frequency component of the Fourier transform, then that thing would extend to a homogeneous polynomial of degree k in omega. So it's it's something not intuitive. That's not what you would think, right? If you just think about the question, but you can verify this. And it turns out that this, together with the smoothness conditions, this is basically equivalent of the moment conditions in the time domain. Remember, we had in time domain for the Radon transform, we had evenness and moment conditions. Moment conditions in the Fourier domain are of this type. Evenness, by the way, is easy. Evenness, even in the Fourier domain, evenness is the same. Just put minus here. It's the same thing as minus here. So evenness is more or less easy. But how does the moment condition from the time domain go to the Fourier domain? It turns out that this is the equivalent of moment condition in the Fourier domain, and it comes from the requirement of smoothness at the origin when you go from polar coordinates to the Cartesian coordinate. So this type of moment condition, this type of conditions you can expect to happens to be working in the circular Radon transform, whereas in the time domain case it's not so easy. So here's one result about the range description in the 2D for the circular transform with the functions supported inside the disk. Again, look how many restrictions I am doing. I cannot describe the range of the circular transform so easily. I'm doing right now it only for 3D. For the circular setup with the support inside the disk. You change any one of these, the situation immediately becomes different and more complicated. Some of them have some results, some of them don't. So if you have a function g, and you want that function g to be the circular Radon transform of some other function supported inside the disk, then the following conditions should be satisfied. In fact, they are necessary and sufficient. So first of all, if your function, you want your function to be compactly supported and smooth, the G has to be compactly supported and smooth. That's natural. These are the moment conditions. It says that, see, now these are moments with respect to the Fourier coefficients. So in a sense, these are moment conditions in the Fourier domain. So the even moments of your Fourier coefficients up to a certain number, and that number depends on the number of the Fourier coefficient. So for G32, the moments up to 64, the even moments, have to be 0. So these are the equivalents of the moment conditions. And this seemingly complicated thing, and it is complicated, are kind of the equivalent of evenness for the regular Radon transform. And here's what it says. It says that if you compute the Hankel transform of this quantity, it has to have zeros exactly at the same locations where the Bessel functions do. And if you go back to, I don't know how far it is, the inversion formula, I may have to go a little bit too far. There. So you see, what I'm saying is that this quantity has to have zeros exactly at the same place where this guy has. Well, it's obvious. You don't want to have zeros in the denominator. Whenever you have zeros in the denominator, you want to have them in the numerator to be able to cancel them so that you have meaningful thing outside of it. The necessity of it is kind of clear. The hard part about the result was that it's also sufficient. So and it turns out that, no, first of all, these two are all that you need, and there was another 2-3 years of work to check, it wasn't in this paper, to see whether these conditions are independent or whether one of them involves the other, because they are not so obvious. You don't know if in some convoluted way one leads to the other. It turns out that for 2D they are independent, and there are similar results in higher dimensions where there is some correlation between this type of conditions and this type of conditions. There are also, there is a range description for the same spherical type setup by Professor Rakesh and David Finch, where they use wave equation, and they have the range description in terms of some solutions of the wave equation. And as I said, there are some results of this type also in higher dimensions by Peter Kuchman, I think Todd and Finch.
Agranovsky and
Agranovsky. Yeah. Okay, so I'm out of my time, and this is luckily the last slide. So thank you for your attention, and thanks for being such a nice audience. Okay. Then I'll answer all the questions outside with the team.